Alright, so we have a question here. We have a function, a map the set q to q cross. The function is defined as f at x is equal to x cubed comma x to the 4. Answer the following questions regarding the above function. We need to prove whether this function is injective, surjective, or invertible. Now, recall that for a function to be injective, or in other words, one-to-one, then it must follow this definition. Function f defined to map a to b is injective if and only if for every a1, a2 element of a, whenever a1 is equal to a2, then it means that a1 is equal. So let's write that in a more mathematical way. And perhaps this might help you to understand. What we are asking is, our function f is injective, okay, and then if and only if the bijection, if and only elements, or any element, which we say for all elements, a, b, two distinct elements from the initial set that it works on, or what we call the domain, if at any point we have that f at a is equal to f at b, if this statement is true, then this must imply that a is equal to b. So that's the actual exact mathematical definition of injective. For surjectivity, or on to, then a function that maps a to b is surjective if and only if for every b there exists at least one a such that f at a is equal to b. Okay, so this says that f is surjective if and only if for all b element of the what we call the codomain there exists some element a that's a part of the domain such that f at a is equal to b, which means that all elements a are defined with some output b. Or actually, no, the exact definition is that all outputs b are defined or mapped by some input a. Okay, and that distinction will become more clear with the next few questions that they answer before answering our central point. So what is a function in mathematical terms? In terms of a exact definition of functions, we have that a function is built what we call, let's say, a label. Usually we use single letters because that's easier to identify instead of a whole jumble of letters, right? Because then you could misidentify this as 4 different functions instead of just one function. Okay, so we label them with a single letter, and then we identify their input domain and their output codomain. Okay, and there's a few additional terminologies you need to know. So on top of this labeling that we have 2 sets that this function uses. There's one called the domain, which will be the inputs. Okay, so the domain defines all elements that can be used for the input, and the codomain shows or expresses all outputs that are possible. Okay, and what a function is, besides the labeling, is a sort of transformation. So what happens is, in some way, our domain values are transformed into our codomain values, okay? In some event, we'll say, or some event slash some transformation, okay? And through this transformation, we convert values from our domain to our codomain. There's a few more notation or a few more terms you should know, and that would be the following. Another name, sort of another name, so we'll put 2 arrows for the codomain, is what we call the image slash range, okay? And the distinction between the codomain and the image or range is that sometimes, often, our codomain is not fully reached. What does that mean? Let's take, for example, a function you should know, f at x is equal to 1 over, and this function here is defined with the label f such that it maps all real numbers, okay, any number at all, to all real numbers. Now, you might say, well, yeah, it does map all real numbers to all real numbers. The issue is when we have x equaling 0, okay? Which means that when we have x equals 0, we basically have the phenomenon where we have 1 over 0, which is equal to infinity. And that's not really allowed for us, okay? Which means that x equals 0 is not part of our domain, technically, the actual domain. Even though we define it as the domain, x equals 0 is not part of it. Thus, f at 0, or what we can call more clearly 1 over 0, is not part of our codomain, okay? And these actual values are defined by the image, okay? So we'll say these are the actual values, all right? And working backwards from the domain and codomain, there exists another term called the pre-image, okay? And the pre-image is, again, a smaller set, or the actual set of numbers that map to the image. However, in terms of the domain and codomain, you're meant to analyze from the domain to the codomain. In terms of the image, you map from the image, or analyze from the image, to the pre-image. So the pre-image, we'll say PI, is a subset, okay? It's a subset, and it's always a subset of the domain. And the image is a subset of the codomain. Okay, we'll say CD. Now, a special event happens when we have our codomain being equal to our image, okay? When our codomain is equal to our image, we can say our function is surjective, okay? What that means for us is that every output is reachable by every input, okay? That's what it means when our image is equal to our codomain, which also implies that our domain is equal to the pre-image, okay? So that's something you should know. All right. So now we know what a function is, what a function can do, and how do mathematical functions differ from the general notation, or the general notion of a function, okay? And a function with a single output versus more than one output, we can see sort of through here. We'll say f at x, y, is equal to x squared plus y squared, meaning that we require two variables to complete one output, okay? And this definition of this function would be in the form, we take two real numbers and we map that to a single real number value, okay? Because the addition of two real numbers will give us a singular real number. We can call, let's say, z. So z here is our summed real numbers, whereas r cross r is our two unknown input variables, okay? We know that now. Codomain and domain, we know now. Rational numbers are any number that can be expressed as a whole number. Can be expressed as a quotient, so a over b, whereas irrational numbers cannot be. So for example, square root of 2 is a non-ending number. Pi is a non-ending number. But though 2.33333 onward is a non-repeating number, we can express this as, I will say 0.333. This is expressed as 1 over 3, right? So this is rational, whereas these are irrational. Now, roots and powers. Okay. Powers and roots you should understand, but something you should take note of is that x to the n and the nth root, okay, when our n here, we'll say this is the nth root actually, when n is even, all x's are positive, okay? When n is odd, all x remain the same, meaning that if we have a negative number and we have an even power, so say 2 to the n, this 2 to the n will always give us another positive number, okay? Because that'll be the same as negative 1 squared times negative 1 to the n. Sorry, no, that's actually the case. Because they're multiplied, be negative 1 squared to the power of n, right? And this negative 1 squared is positive 1 power of n, and that's that. Now if we have an odd number, 2 to the n plus 1, then this is the same as negative 1, 2 to the n times negative 1 to the 1. This will be negative 1 times 1 to the n, okay? Which you can express as negative 1 to the n plus 1, which means that if our initial number here, which I wrote as negative 1, but it could be whatever it wants to be, if it's negative, it'll stay negative for even numbers of powers. And if it's odd power, then it will stay positive or negative. And negative quotients, let's say we have x to the negative m over 2, or negative m. You just express that as x to the m positive. Okay. Composition functions, you can sort of infer. There's not really a lot of composition to this problem here, so we won't discuss that. Okay, so for this function here, f at x is equal to x cubed, comma x to the 4. How can we prove that it's injective? So for us to prove that this function is injective, we rely on the exact definition once more. So for all AB element of Q, our input space, if at any point we have f at A equaling to f at B, equaling to f at B, and this implies to us that A is equal to B, so let's prove that. Now here, because we have two outputs, it's almost multivariable, but not really. It just has two outputs, or its output is a pair of two values. We'll have to make two different boxes. Here's box 1, and here's box 2. Box 1 will be box 1 will deal with the x cubed, and box 2 will be worried about. Now for x cubed, we have basically two inputs, A and B, which means that we'd have possible outputs of A cubed and B cubed. And we want to prove that these two values are the same. Okay, now recall that for powers that are odd, the signage remains, which means that if A is positive, then A cubed will be positive or negative. And if A is negative, then A cubed will stay negative. The same follows for B. Okay? It means that if these two both, that signage, we can take the cube root of both sides, and we get that A is equal to B. Okay? We know this for a fact based on how cube roots work and how powers work. Using this fact, which we know to be true, we can aid ourselves in this proofing here. Okay. Now, given that we have two inputs AB, or two possible inputs AB, then we have A to the 4, which is equal to B to the 4. And we're trying to prove this to be true. So if at any point we have a contradiction, then we are proven wrong. Okay. So let's try the same method. We'll take the cube root or quartic root of both sides. We get that A is in fact plus or minus A, and B is plus or minus B, because we cannot actually guarantee the signage of the original function, original value, because we have an even power. So our original value could have either been positive or negative. By using the fact that we know that both values are equal, we can actually say here again that A and B are equal, right? Because if you sort of expand on this, if A is less than 0 or negative, then B must also be less than 0. If A is greater than 0, then B must also be greater than 0, which means that they share signs. Okay, which means their signs would cancel out if they are the same. Thus, A has to be equal to B. So we have proven that it is, in fact. Now let's try and prove surjectivity. In terms of surjectivity, we go back to the definition, which tells us for all values of, let's say, well, because here we have a multi-output here, has a pair output. We'll make a pair here. We'll say C comma D, element of Q cross Q. So for every output, there must exist some input, which we call alpha. Of course, it's an element of the input space, Q, such that F at A is equal to the pair CD, right? Now, an easy way to disprove something is to find a contradiction. Because unless a theory is true for all cases, it is not a theory, it's just incorrect. Alright, so all we have to do is to disprove that this is surjective with one counterexample, and that's it. We can be finished with our... So for us to find a counterexample, we need to find some instance in that where our input alpha cannot map to some output CD, okay? And we know this takes the form x cubed comma x to the 4, right? Now immediately here, you can say that, the x cubed maintains the signs, right? However, our x to the 4 here does not, okay? Every value it gets, so alpha, must be positive, which means, for example, the pair 2, we'll say we had alpha being negative 2. That means our pair would be 2 to the 3, negative 2 to the 3, comma, negative 2 to the 4, right? Which would be then 8, or negative 8, comma, positive 16, right? So this is what we got immediately from the function. But we couldn't have the pair negative 8, comma, negative 16, right? There's no way for us to do this. Right, that doesn't make sense for us. Because here, if this had been negative, then it means our function x to the 4 gave us a negative number, which we know is not possible because from calculus, we can sort of graph in our head what x to the 4 looks like. It looks sort of like the quadratic because it's an even power. And we know that's defined for all positive outputs, okay? Non-negative outputs. So we know this value is impossible. Now the issue is this counter example is completely viable. However, there's an issue with how the question was posed, okay? We assumed that alpha must assume values from the real numbers, right? Well, what does that mean for us? Okay, for us that means alpha can only be any number within the real number set, okay? But that's not the case because we've been given some arbitrary set Q, which means that although this is true for real numbers, we don't know with certainty that this element does not exist for us, right? We don't know for certainty that this element here cannot exist for us. Okay, so now we have an issue. Let's find a more concrete counterexample. Okay, for a more concrete counterexample, begin. We'll say this time we're looking at beta, and this beta must map to pair EF. We'll say EG. Okay. Again, this is given by x cubed, comma x to the 4. Okay, what does this mean for us? Well, again, we know that this only gives positive and negative numbers, and this gives us only positive numbers. Another unique thing about x to the 4 is that x to the 4 behaves somewhat like x squared, okay? What does this mean for us? Okay, let me take an odd number. Let's say 3, okay? And then you square it. This gives me 9. Okay, let me square this. This gives me 81. Okay, now let's say our beta value was equal to 3 and 9. Okay, sorry, 3, which means I'd get the pair. This would be the same as 3 times 3, which is 9, times 3, which is 27. 27 times 3 is 20, 40, 60. I don't know. 84, I think. Right, 60, and then 7 times 3 is 21. Yeah, so 81. Oops. 81. Okay. So we get the pair 27, 81. Now, let's say I don't want to work from the beta value. I want to work backwards. Right? I want to get some pair and try and find some value that our function could have given. Okay. Now again, our one input is given by x cubed. So our function x cubed will look like this. And then our function x to the 4 will again look like this. Okay, sort of squish down. What does this mean for us? How does this help us? Okay, we can already sort of see discrepancies between this function. Right? We already know this part does not match here. Right? But there's also something else. There's a few values here because of the step nature of the quartic function that the cubic does not have. Okay, despite it also being a step function or step-like. Okay, let's take, for example, an even number. The only reason I'm sort of dodging around the answer here is because I want you to build an intuition to get this answer on your own. Let's take one even number from our function x to the 4. Right? So we'll take the 4th root of both sides, and you get that plus or minus x could have given us to the end. Okay? Does this make sense? Well, I guess it does, yeah. If we have, let's say, 16, 4, then this could have given us plus or minus 2. Now let's look at this one more time. If our x to the 4 value is 16, that means our x to the 3 value is 8. Which means that 8, 16 is a possible pair for us. Okay? Now let me look at another pair. Let's say I want 3, an odd number from x to the 4. Okay? This makes sense for us. Now, what can we do? That means that we must have the 4th root of 3 is equal to x, right? Or plus or minus. So what does this mean for us? Okay, sorry, going back to here, this means that we have two possible pairs, negative 8, 16, and 8, 16, okay? Here we have two possible pairings, negative 4th root of 3, comma, yeah, it'd be this to the power of 3, or we could have positive of that. So 4th root of 3 to the power of 3, comma 3. Right? These are both possible pairs. Now, this pair looks overly complicated. Let me consider this pair here. We are saying that these two pairs are possible. Can I now say that this pair is possible? Well, let's check. I want 7 to equal x cubed, which means that you have the cube root of 7 is equal to x. Thus, it means for this to be a part of the function, cube root of 7 to the power of 4 must give us the x to the 4 value, right? This value here. But we know for a fact that there's no way that the cube root of 7 to the power of 4 gives us 16 in any way. This is where our contradiction comes in, or our counterexample. Find one valid pair and then decrease one of the values by 1. We could have instead done 8, 15. This pair is unreachable by our function, okay? And this goes back to our stepping pattern, right? So there are some values that are inherently impossible to reach with this pairing, okay? Because we rely on the same value x. If this had been like xy, so x cubed y to the 4, then this could be possible. But because we're relying on the same value, it must be that x cubed is equal to x to the 4 in some way, okay? So 1 is equal to x. That's when these two values are the same. So all we have to do is find one counterexample, and thus we've disproven its surjectivity, which means this function is not. Hopefully I did a good job of describing how I got there. But basically find a valid pair, decrease one by one, decrease one of those values of the pairs by 1, and you will find an unreachable pair. That's only when these two pairs are linked by the same variable. So we can go back to the original question, and it asks us whether it is injective, and we did provide the relevant justification. And is it surjective? Yes, we provided a relevant counterexample. Sorry, no, it's not. Now, invertibility. Invertibility means that a function f that maps from a to b must have a counterpart f inverse such that it maps b to a, okay? But this other counterpart, this little twin of theirs, exists if and only if f is what we call bijective, okay? I'm going to write it as bij because I'm too lazy to write the entire thing, but bijectivity. Bijectivity is a label we give to a function only when they are both injective and surjective. Now in our case, it is only injective, not surjective. Thus our function is not bijective, thus it's not invertible, right? Because for a function to be bijective, that means that all inputs map to all outputs, okay? Right? There's a one-to-one correspondence between both, which means that we are actually physically able to make that inversion, right? Because we are allowed to. This inversion is allowed for us because we have a way of mapping all outputs to all inputs in the reverse order. So through we call it reverse transformation, right? The same way that a function performs a transformation to map one input to an output, a reverse transformation will take that output and go back, but that requires both the input and output to exist and be defined in both ways, which is why bijectivity is required. So here we put it is not, and that is it for this question. Hopefully that helped.